A spinning spherical shell. A uniform 8.4 kilogram spherical shell, 50 centimeters in diameter, has four small 2 kilogram masses attached to its outer surface and equally spaced around it. So these are the four masses. This combination is spinning about an axis running through the center of the sphere and two of the small masses. So these two masses are on the rotation axis. What friction torque is needed to reduce its angular speed from 75 rpm to 50 rpm in 30 seconds? So we have to start with figuring out the moment of inertia for rotations about the center of mass axis, so that goes through its center. So if we look at a spherical shell here, you can see that when I'm at a distance capital R from the origin, if I go through an angle r d phi, this is going to give me the arc length, and then the other dimension will be r sine theta d phi. So I have two things here. So for the rotations about the center, I'm going to have, so let's try to do this nicely here. We have for this one, if this is our capital R, this is our angle d theta, r d theta, and then for the other dimension here, we would have rotation on for the projection of r on the xy plane. That would give us r sine theta d phi. So we take the projection onto the xy plane. So we obtain here r sine theta, and then we rotate it by an angle d phi. So that gives us this side. So this angle here is d phi. All right. So then this completes this area element to be r sine theta d phi times r d theta. So for the mass density, for a uniform spherical shell, we have areal mass density, total mass capital M, divided by the surface area 4 pi capital R squared, surface area of a sphere. So we obtain I, center of mass, rotations about the center of mass axis, given by integral r square dm. Now I look at the distance between this mass element and the rotation axis, which is the z-axis. That distance would be r sine theta. So I would have moment of inertia is equal to sigma times integral r sine theta square sigma dA. So sigma times dA. So if I continue with this calculation, this is going to become, my sigma is capital M divided by 4 pi capital R square. Then I have the integral over theta and phi. Phi integral is from 0 to 2 pi. Theta integral is from 0 to pi. So I have r square sine square theta. Then for the area element, I substitute r sine theta r square sine theta, r square sine theta d theta d phi, so that this is going to become capital M divided by 4 pi r square. The r to the fourth power comes out. The phi integral gives me 2 pi, but the theta integral from 0 to pi of sine cube theta d theta remains. And for sine cube theta, I have to substitute 1 minus cosine square theta, that's sine square theta, times sine theta. So this is going to become, so this becomes r square, and here I have 2 pi, making this 4 pi 2. So this becomes capital M r squared over 2 integral from 0 to pi sine theta minus sine theta cosine square theta d theta. Why should theta go from 0 to pi? So if theta goes from 0 to pi, we get this slice, and then we rotate this slice by an angle 2 pi to cover the full shell here. So that makes perfect sense. Now if we perform this integral, this is going to give us capital M r squared over 2. The integral of sine is minus cosine, and if I call u as cosine theta, du is minus sine theta d theta. So this becomes integral of u squared du. So this will be replaced with u squared du. And integral of u squared du is u cubed over 3. So this becomes plus cosine cube theta divided by 3. This is to be evaluated between 0 and pi. So that gives us mr squared over 2. So when I evaluate cosine theta at pi, I obtain minus 1. So this is plus 1, and cosine cube pi over 3 is minus 1 over 3, minus cosine 0 is minus 1, plus cosine 0 cube over 3 is 1 over 3. So this gives us mr squared over 2 multiplied with 1 minus minus 1 becomes 2. So we have 2 minus 1 over 3 minus 1 over 3. 2 minus 2 over 3 gives us 4 over 3. So the answer is 2mr squared divided by 3. This is the moment of inertia of a uniform spherical shell. Now, what is the total moment of inertia for the rotations about the center of mass? It's going to be 2mr squared over 3. That's the contribution coming from the shell. And we have each of these masses a distance r from the rotation axis here, the spin axis. The other two are on the axis, so r squared dm would give us 0 because r would be 0 for those masses. So we have two contributions, 2m r squared, where m is the mass of these guys. So this one has mass capital M, and these are the lowercase m's placed equally spaced around it. So if we substitute the numbers here, 2 times, what is the mass of the spherical shell? It's 8.4 kilograms. So 2 times 8.4 multiplied with radius squared over 3. What is the radius? It's 50 centimeters in diameter, so 25 centimeters radius. So 0.5 meters over 2, that's the radius, squared divided by 3, plus 2 times, these are 2 kilogram masses, 4 small 2 kilogram masses, 2 times 2 times capital R squared, which is 0.5 over 2 squared. So this gives us 0.35 plus 0.25, which is 0.6 kilograms meter square. And you should notice that there is no contribution from the top and bottom small masses. Okay, because they're right on the rotation axis. Now, we want to change its angular speed from 75 RPM to 50 RPM. So our initial frequency, F1, is 75 revolutions per minute. That is 75 revolutions in 60 seconds, 75 over 60 hertz. That corresponds to an angular speed 2 pi times the frequency, 2 pi f1, 2 pi 75 divided by 60, which is 2.5 pi radians per second. The frequency that we want to reach, f2, is 50 RPM in 30 seconds, so we want to reach this frequency. 50 RPM corresponds to 50 revolutions divided by 60 seconds, 50 over 60 hertz. That gives me an angular speed 2 pi f2, which is 2 pi 50 divided by 60, and that's equal to 5 pi over 3 radians per second. The angular acceleration I'm looking for is delta omega divided by, it's delta omega divided by delta t, constant angular acceleration. Final angular speed is 5 pi over 3, initial is 5 pi over 2, 2.5 pi, and I want to go there in 30 seconds, so 1 over 30. So this angular acceleration is minus 5 pi divided by 180, which is minus pi over 36 radians per second square. All right, and this corresponds to a net torque. Now we have to calculate the net torque. Net torque will be equal to I alpha, I total times alpha, Newton's second law rotational form. So we will have minus 0.6 times pi over 36, which is minus pi over 60, which is minus 0.0523 Newton meters. So the minus sign indicates that we are basically slowing down. So this is not an angular acceleration, it's angular deceleration. That's what it means basically. Okay, now to summarize, we have a spinning spherical shell. There are four masses equally spaced that are attached to its outer surface, and two of these masses are on the spin axis, two of the masses are at a distance capital R from the spin axis, and this starts spinning around the spin axis. What friction torque is needed to reduce its angular speed from 75 rpm to 50 rpm in 30 seconds? First, we have to determine the moment of inertia of a spherical shell. Now, for the spherical shell, we have two dimensions on an area element that is r sine theta d phi and r d theta, the arc length. So that's the dA. The mass density, on the other hand, sigma, is capital M divided by the surface area of the sphere, 4 pi r squared, for a uniform mass distribution. And when we calculate the moment of inertia for rotations about the center of mass, integral r squared dm, this r is the distance between the mass element and the rotation axis, so that distance is r sine theta, so it's r sine theta squared dA. So the rotations, this integral should go from 0 to pi for theta, so that we get this slice, and then we rotate this slice throughout the xy plane here by varying phi from 0 to 2 pi. So 0 to 2 pi phi integral, 0 to pi theta integral, r square sine square theta, that's integral r square, and dm is basically sigma times dA, r square sine theta d theta d phi. So this integral gives us 2mr square over 3, where we played some tricks with the integration. Now the total moment of inertia comes from the moment of inertia of the sphere plus the two small masses, point-like masses, 2 kilograms that are at a radial distance capital R from the spin axis. These two masses have no contribution because their distance from the spin axis is 0. So we have 2mr squared over 3, capital M, capital R squared over 3, plus 2 lowercase m r squared, which is the contribution from the two small masses, 0.6 kilograms meters square. Now, initial frequency 75 rpm corresponds to 2 pi f1, 2.5 pi radians per second. The frequency we want to reach, 50 rpm, corresponds to 5 pi over 3 radians per second. The angular acceleration that is needed is delta omega over delta t, which is minus pi over 36 radians per second square. This minus sign indicates that it is a deceleration. And the net torque is equal to I alpha, that's minus 0.6 times pi over 36. 0.6 was our total moment of inertia, so we obtain minus 0.0523 Newton meters. So this minus sign indicates that this is basically a friction torque.